Okay, great. I am going to start by actually dropping a link to a Google Doc into the chat uh, that hopefully you should all be able to access. Let me know if the sharing permissions are wrong, but throughout this presentation, I'm going to reference various papers and GitHub repositories and such that are related to this work. And this is just a place to have it all in one section where you can see it all. So hopefully that works out okay. And I will note that at the bottom of that, just a shameless plug, at the bottom of this Google document, my division with the National Park Service is hiring a bioacoustics intern in the summer of 2022. So if you or anyone you know might be interested in that, it's a 12-week internship that could be remote or based in Fort Collins, Colorado, here with me. Let me know or share it around. And other than that, I think I'll just kind of get started here. I'm going to talk for about 40 minutes or so, 35 to 40, depending on how excited I get. And then hopefully we'll have some time for discussion and knowledge sharing and such. So I'm going to kind of exit out of the chat window, and feel free to throw questions in the chat as the spirit moves you to do so, but I will probably save questions till the end. But otherwise, yeah, if anything goes wrong, Dina, feel free to jump in and let me know.
All right, I will.
Okay. So yeah, today we're going to be talking about a paper that I wrote when I was based at the University of Vermont about the software package AMMonitor, remote monitoring of biodiversity in an adaptive framework with R, which Laurel passed along in the announcement for you all. So my name is Cathleen Balantic, and I'm currently working as a biologist specializing in bioacoustics at the Natural Sounds and Night Skies Division with the National Park Service. But previously, at the time of this work, let's see if I can advance my slides here. At the time of this work, I was a PhD student and later a postdoc at the Vermont Cooperative Fish and Wildlife Research Unit. And I am no longer, I'm not the package maintainer on this. I'm not the person kind of taking it into the future anymore, but I have a couple of colleagues here today. I saw Larry Klarfeld is on. I'm not sure if Terry Donovan is also on, but they are based with the Vermont Cooperative Fish and Wildlife Research Unit, and they are taking AMMonitor into the future to be basically bigger and better and more efficient. And we can talk more about that at the end of the presentation. Oh, and just a quick note, is this presentation being recorded?
Yes, it is.
Okay, awesome. I know I have some colleagues who can't make it who might want to see it as well. So yeah, that's what I'll be kind of talking about, some of my previous work on this, and I still use the package every day in my own work, and you can see all of the various contributors who have supported this work at the top here. And we'll move along. So yeah, so this paper, we wrote it in 2020, and it was published in Methods in Ecology and Evolution. It should be linked in that resource sheet I dropped in the chat. And the AMMonitor software package is really, it's not meant to be an exploratory software situation. It's really meant to be driven by a pretty clear hypothesis and or management objectives. So you start with a management objective or a hypothesis, and then you collect your data, which in this case, I'm going to be talking about acoustic monitoring data. You might be collecting other data at your sites as well. You've got some type of external storage that your data gets piped to, or it might be cloud storage. And then your raw and processed data and stored analyses will more or less be stored in a SQLite database, and that will help support systematic reporting and data summary that sets you up well to be able to compare your monitoring results to your management objectives. And I'm going to step through the 3 routines that we talk about in the paper. It's meant to be a pretty flexible package. There's a lot you could do with it, but I'm going to talk about 3 of the things that I've done with it. And the first routine is around temporally adaptive sampling here in the upper right-hand corner. I'll talk about automated detection of target signals. And I'll also talk about bringing that all back to the idea of being able to, in a streamlined way, compare your results with your management objectives. So before I dive into that, though, I kind of have to set up the background story here. So when I was doing this work, I was a PhD student based at the University of Vermont, but my field site was in Southeastern California here. I was partnered up with the Bureau of Land Management, and this particular site was called the Riverside East solar energy zone. And it's still called that because it still exists. And it has been slated for utility scale solar energy development. And it's about 150,000 acre landscape. And Bureau of Land Management lands are typically multi-use, multi-objective landscapes. So in addition to solar energy development, an example of a management objective on this landscape might be that as solar infrastructure comes in, the solar farms, transmission lines, potentially some distribution lines, service roads, access roads, we have certain wildlife species that might end up benefiting from this human infrastructure, such as the Eurasian collared dove, which is considered invasive in this area of the country and will displace other doves, and then also coyotes, which will follow the roads in and benefit from all the water that gets impounded by the roads, and then they'll eat up all sorts of sensitive lizard species. And so an example of a management objective on this landscape would be to minimize their occurrence across the landscape as this solar development comes in. And then meanwhile, we might have species like the black-tailed gnatcatcher, which by some is considered an indicator species, not too tolerant of too much human development and encroachment. And a management objective on this landscape might be to maximize their occurrence across the landscape. So one way we can measure our progress toward this type of management objective is using a dynamic occupancy model. And I know we've had some sessions in the past focusing on occupancy, so I'll keep this pretty brief, but just to make sure we're all on the same page. In a dynamic occupancy model, we're going to be taking some statistically relevant sampling of points across the landscape and trying to figure out whether they're occupied in black or unoccupied in white by a species of interest. And the word dynamic means that we're not just doing this in one season, we're looking ahead to the next season and we're sampling again, and we're looking ahead to a third season and kind of looking through time at these dynamics. And eventually this can set us up potentially to link back to management on the landscape, set us up to be able to have a model that can allow us to predict the consequences of a management action on any of our species of interest. And in this case, the management action that I'm talking about in this example is solar energy development. And this type of framework sets us up really well to be able to conduct adaptive management potentially, which is an approach of great interest to a lot of federal agencies and a lot of different land management agencies right now, where we're able to use iterative learning to reduce uncertainty over time and improve our management decisions. And I just want to point out that the AM in AMMonitor stands for adaptive management. So it's part of a suite of different packages that have come out of the Vermont Co-op unit that are trying to support, trying to come up with tools that can support adaptive management, because adaptive management's easy to talk about, it's a great vision, and then it's really hard to pull off in practice if you don't have the tools to support it. So that's kind of where we're coming from with this package. Okay, so now I can kind of jump into the routines in the package that we talked about in the paper. How do we actually get to adaptive management from here? We're back on this solar energy landscape. So when we were early on in the process of talking with the Bureau of Land Management, we noticed that a lot of their species of monitoring interest were species that could be detected based on vocalizations or sounds that they produce. So we pitched the idea that we could put some audio recorders out onto the landscape and just do a proof of concept, a rapid prototype, and see if we could monitor some of these species acoustically. And they said, go for it. So we ended up building our audio recorders out of smartphones. We attach an external microphone and we attach a solar panel for power, which is really handy in this landscape in a solar energy zone. And in this initial iteration of the project, I ended up learning a lot about electronics and doing quite a bit of soldering. And we got into the internals of the phone as well to figure out how to turn it into a reliable, scientific, autonomous monitoring unit. And we ended up with a prototype of 20 remote acoustic monitoring units that we installed in this solar energy zone. And the huge benefit of using cell phones for this purpose is that we were able to take our audio recordings. We took 1 minute at a time audio recordings, and we were able to transmit them over the cellular network. And I had access to them the next day, 3,000 miles away in Vermont. And obviously you couldn't do this in a wilderness area, but we had enough signal out there that we were able to pull this off. It was really handy. It was really nice to be able to, see that a certain monitoring unit wasn't collecting data anymore and needed to go be serviced. So this was really, really neat that we were able to pull it off. But a big drawback of using smartphones for this kind of purpose is that data plans are expensive. So we went through, we did the math, and turns out we could record for about 9 minutes per day per phone, which on the one hand, if you're someone who's used to taking continuous 24-hour recordings, you're probably thinking, oh, that's like hardly any data at all. But the problem I've set up at the beginning there was an occupancy problem. And that was really where we were at in terms of the type of challenge we were trying to solve. So 9 minutes per day is actually a lot. If you've ever done like a point count in the field for birds, you might be at your point for 5 or 10 minutes a week gathering data. So 9 minutes per day for an occupancy problem was really more than enough. But the challenge that we had was that we had this sort of diverse cast of characters here that were going to be available under different conditions throughout the day and throughout the year. And don't worry too much about who's who, but some of these are going to be vocally active during the day, some maybe during like a dawn chorus type of situation or during daylight hours. Some of them are going to be detectable more at night or perhaps more on a crepuscular dawn and dusk basis. Some of them are migratory. So there was kind of this question of maybe we could capture arrival and departure dates, or maybe we had to make sure that we weren't, sampling too early or too late in the season for them. And then finally, we had a species that was only going to be active under extremely specific conditions. The Couch's spadefoot is a desert amphibian. It's a toad that's only going to be out and calling after like the first monsoon rain approximately in late summer or early fall. So that's the only way you're going to know that they're there acoustically. So it was kind of an interesting spread of different focal species. And that sets us up for the motivation of one of the routines that I talk about in the paper, that motivating challenge that we're monitoring multiple species. They're available under different conditions, and we have this limited sampling budget. So our solution to that was to develop a way to optimize and automate the sampling resources we do have. How do we allocate those 9 minutes per day as efficiently as possible and make sure we can meet all of our monitoring objectives? And so we had a prototype of 20 phones. They were not situated statistically on the landscape. So we ended up exploring this in a simulation setting, which is detailed in one of the papers in that linked Google document. But we also, I will say that we also figured out the mechanics of how to do this in the field and, how do you make the hardware do what you want it to do and so forth. But just, I'll talk through this. We developed this temporally adaptive sampling algorithm, and it really allowed us to optimize our sampling resources. And what we do is we start with species vocalization models. So you have to know something about when you think your species is going to be active. You can build these based on the literature, based on your own expert knowledge, based potentially on your own audio data. And the models will incorporate variables like this, like what do I think the probability of vocalizing is going to be on this day of the year or this day of the year? What's the probability of vocalizing this hour of the day or that hour of the day? We also, in our models, we incorporate things like wind or rain as well. So you can incorporate weather variables too. And in this case, we compare these species vocalization models with the daily weather forecast at each site. And then we output a customized Google Calendar for each site for each day. And the way that this works, I have like a little visual to sort of show you how it works. But it's based on kind of a classic capture recapture math. So what we do is we start the beginning of the sampling season with each species having an equal priority weight in the algorithm. And on the first day, we collect data, and then we're probably going to start detecting some of these species on our audio recording. So some of these species weights are going to drop because their probability that they've been acoustically captured is going up. And so we keep sampling through the season. Some of these species are now dropping out of the prioritization scheme altogether because we are so confident that we've acoustically captured them on a recording previously that we don't even need to worry about sampling at a time of day when they're available anymore. So we keep sampling. By the end of the season, we're not even worried about capturing day birds anymore. We don't care about any other species except this toad, and we can now save all of our sampling resources to try and prioritize capturing this toad. So everything's kind of based on this probability of acoustic capture. And what we found in the paper where we examined this was that it's just an idea that could maybe make your acoustic monitoring a little more efficient depending on what your question is. We found that the benefits, as you might predict, might be highest if you have a short study season or a small sampling budget or a species that's only going to be available under really specific conditions. But something I'm also thinking about is there's a possibility that I think you could apply this type of thinking to existing data that was collected under a continuous or a stationary schedule, and maybe it would reduce search time. So yeah, that's one of the routines that you can kind of look at in this AMMonitor R package. If you want to know more, there's a whole separate GitHub repository and there's a paper associated, and that's all in the resource sheet. And then this figure from the paper just kind of summarizes this temporally adaptive sampling idea where you're prioritizing monitoring targets and there's functions that are associated with that. You're creating activity models for these monitoring targets, and then you're generating a sampling schedule, which is based on activity models, potentially based on the weather forecast, and really based around this cumulative probability of capture. So that's kind of the first thing I was going to talk about. And the second one is this automated detection. So I'm just going to lay out a scene that's probably pretty familiar to those of us who are deep down in the acoustic monitoring space, where you're sitting there, you've got your headphones on, you're listening to an audio recording you took in the field, and you're using your software of choice to maybe pan through a spectrogram here with time on the x-axis, frequency on the y, and signal intensity kind of coming out towards us on the Z, and you're going through and you find, hey, this looks like my focal species. And depending on what your research is, you might be drawing boxes around every single instance of your focal species that you find. And you're going through and you're manually annotating your data. And this is great depending on what your question is, but I'm sure we've all been there where all of a sudden more and more data is coming in, you're drowning in data. What's the next thing you're going to do? I think we all know the answer. We're going to try to make the computer automatically detect these sounds for us. And anyone who's dabbled in this knows that it is full of challenges and opportunities. But so AMMonitor has tools to try and do this as well. So it looks something like this. You have your spectrogram here, and this little yellow blob that we're looking at here is called a template. So we have some template-based matching algorithms that you can use in AMMonitor. And I should mention that AMMonitor, this portion of AMMonitor is built on another R package that you might have heard of called Monitor, which was also developed by the Vermont Cooperative Fish and Wildlife Research Unit. So in this package, we have two template matching algorithms that you can play around with. One of them is spectrogram cross-correlation, and one of them is binary point matching. I'm not going to go too far into the details, but more or less, it's kind of a low barrier to entry way to build a detector. You just need to know what your species sounds like and kind of what it looks like. You can more or less draw a box around it, and you can play with things like density of points and buffers and things like that. But once you have your template, you can then use it to sweep through a new audio recording here and detect similar signals. So every little red box here is a detection with this template that we made on the previous page. And I know a lot of you know this already, but we might have folks who have joined from other places. So I'm going to go through kind of the 4 outcomes that you can have when you sweep your template through a new audio recording. You can either have a true negative here, TN, which is where species wasn't vocalizing, we didn't detect anything. That's fine. We can have a false negative here where the species vocalized, we failed to detect it with our detector, and that's a mistake. Or we can have a false positive here where these horizontal bands are a little bit of electromagnetic interference in the recording, and it was enough to trigger this false positive FP here. That's another type of detection mistake. And then finally, we have true positives. Species was vocalizing, we detected it. Those are great. And depending on what the question is, like if we're just looking at a question of occurrence or detection, non-detection, this outcome is fine, right? Like if we're looking at occupancy, the species was present on this recording, it was vocalizing, we detected it. These detection mistakes kind of come out in the wash, but they really become problematic when they're building up in a way that makes you not able to really capture the underlying dynamics on the landscape. So I was struggling in my work with a lot of false positives in this system. My automated detection system was producing a ton of false alarms. False negatives were not as huge of a problem. So we've got some target signals here on the left, and then we have a bunch of false alarms here on the right. Our motivating challenge was to just get rid of these false alarms, train the system to recognize and eliminate them, and then end up with a cleaner data set to use in your population models. So that's what we tried to do. So we end up with we make a template. I ended up writing another paper that kind of examined this. We ended up looking at 3 different focal species. We ran these templates against the data, and now here you're just looking at all of the detections for this Eurasian collared dove across like a year of data, all of the detections for this Gambel's quail, all of the detections for this verdin, which is a little charismatic little desert songbird. And at this point, we're not sure what the target signals are and what the false alarms are. But while we are running the templates against the data, we are extracting features associated with every single detection. So we're extracting information about the amplitude values of all of these pixels. We're summarizing the data in the temporal direction and in the frequency bins as well. We're picking up zero crossing rates. We're looking at dominant frequency, all these types of kind of canonical features that you would want to extract that are associated with an acoustic signal. And then we're positioned to fine tune the automated system. So in AMMonitor, we have 5 classifiers that we use. So AMMonitor interfaces with the CARET package, C-A-R-E-T. It's by Max Kuhn, and it is basically a machine learning tools package. And we use 5 classifiers from that package in AMMonitor: k-nearest neighbors, 2 types of support vector machine, random forests, and regularized logistic regression. If you've ever heard of lasso or ridge regression, those all fit under this umbrella, or penalized regression or elastic net. Those all fit under regularized logistic regression. And this I actually find, I'll just say as a side note, this is one of the best ones I think that I've found in my work for these template-based matching problems. So we've got these 5 classifiers running under the hood, and we more or less produce a probability that a detected event is from the target species. And in the training and testing phase of this paper, the associated paper that we wrote, we ended up training on only a subset of data because we really wanted to see, what happens if we train on a small amount of data and then see how it does. So we're training and testing on a subset of data. And what we're doing here is in AMMonitor, we have a function that just pops through every single detection and allows you to verify it. So it'll pop up and say, is this a true detection for this species ID? You look, you listen to it. If it's not, you'll label it as a false positive. If you get a target signal, you'll listen to it, you'll look at it, you'll label it as a true positive. And then you end up with a nice, neat pile of labeled data with target signals on the left and false alarms on the right. And you can choose then at this point how much to use for training and testing. In this example, I'm going to use 70% of the data for training. I'm going to use 30% for testing. And then we're ready to assess how these classifiers did. And the metrics that since in a lot of my problems, I'm dealing with a class imbalance where you might have, 90 false positives and 10 target signals. And accuracy is really not a great metric for measuring that, because you could just classify everything as a false alarm and have 90% accuracy in that case. So I don't really look at accuracy too closely. I tend to look at precision, which is, how many of the items that we've classified as a target signal were actually target signals. Sensitivity and recall, how many of the total target signals did we actually find? F1 score is kind of a weighted average between those two. And then specificity is kind of looking more at the false alarms. How many of the false alarms did we identify? So those are the metrics I tend to focus on. And then at that point, we're positioned to see how we did on the rest of the data. So training, testing, and assessment phase. In this particular paper, we were only looking at a subset of data, and then we were testing it for real on everything else to see how it did. And I'll keep this brief. Here, we're just going to look at the results for Eurasian collared dove. So in the background here, we're looking at the total number of false alarms and the total number of target signals in the data set before we applied this machine learning refinement. And after we applied it, we were able to really get rid of a lot of the false alarms. And you'll see that we lost some of our target signals as well. So the sensitivity was only about 0.7 in this example that I'm showing. You know, I'd really like to see it higher, but for the occupancy problem that we were looking at, this was actually a fine result. And I guess the point with respect to the software is that there are always going to be trade-offs. I think anyone who's looked at acoustic automated monitoring like this knows that it's trickier than you want it to be. So yeah, the upshot here is that automated species detection is tricky, but what we have here is one more simple, accessible method for automated detection that allows you to produce a probability that a detected event is a target signal. We might want to mute some folks. I'm getting a little bit of feedback. Okay, so that is really the second routine that we talk about in this paper. And this is just the summary slide again, and it shows kind of some of the functions in the package that are associated with each step. You're creating your templates, you're detecting things, you're labeling some detected events, and then you're training and testing your classifiers, and then you're using your classifiers to make predictions on new detections. So that's kind of the second one. I figure that's probably one that a lot of people would be interested in. And then the last item that we really talk about in this paper really circles it back to this motivational idea I tried to set up at the beginning around these dynamic occupancy models, where we have models that are driven directly by management objectives. We've got this adaptive management vision that's kind of driving the entire package. And in this dynamic occupancy model space, we can get all sorts of interesting parameter estimates around occurrence and also look at the factors that might influence extinction or colonization or detection. And we did write a paper about this as well, which you can look into, but really what we found was that dynamic wildlife occupancy models using automated acoustic monitoring data really look like it's a method that has a lot of potential. In the simulation scenario that we looked at, we found this dynamic occupancy method was going to be robust across a wide range of scenarios. And it was also able to cope even with a kind of not very good automated detection system and a low vocalization rate by the species of interest. So I'm not going to go too far into that, but I'll pull it back to this summary figure from the paper where you're really, oh, sorry, I'm getting too many things are in my way, where you're setting your management objectives. In this case, maybe your management objective is to maximize the occurrence of this species. The indicator we're going to use is occurrence. And you might have a minimum and a maximum occurrence that's acceptable for this species across your landscape. You're going to then conduct your remote monitoring. You're going to perform analyses, and this is one of the functions in the package, which I think is really handy, which is where you can just generate an encounter history based on various combinations of your automated detections, and then feed that into our presence to fit your occurrence models. And then you're ready to really do the thing that you set out to do, which is compare your results with your objectives and potentially trigger a management action. And in this example here, in year one, we're falling within our management window of acceptability. And in year two, we're falling outside this acceptable range. And that is a really clear systematic trigger for management to meet that unmet objective. All right, I've lost my ability to advance. Okay, so that kind of summarizes those routines that we talk about in the paper. And I just wanted to kind of talk about, now that I've moved on from the co-op unit and I'm working for the National Park Service now in the Natural Sounds and Night Skies Division, and I am using this package every day still. So we've got a couple really interesting Songbird phenology projects. And here I'm just showing you some data taken at Lewis and Clark National Historical Park, where we're trying to figure out, when are the birds really active? We're looking at 3 focal species in this example. And I used that automated detection routine where we create a template, we label the data, we train the machine learning classifiers, and then we have a refined data set. And here what I'm looking at is really a much different problem. We're not looking at occupancy anymore. I'm looking at a finer grained problem where I'm really trying to be able to capture the trends through time of vocal effort by the species. And it's working out really well. So I think it's really fun to see. I'm really excited to look forward into future years and see how these curves might be shifting. But you can see how the Pacific wren here in pink is really peaking in early May, and then it's tapering off. And then we have this migratory species, the Swainson's thrush, is coming in and really dominating the soundscape here in kind of around the summer solstice, and then tapering off. And then the Wilson's warbler is really just less vocalization activity in general from that species. But in this case, I had to worry a lot more about false negatives. And so here what we're looking at is I kind of went through and manually annotated a subset of this data to compare it to the automated detector and see how that was doing. And you can see here that these automated detectors, so again, the blue is the truth, the red is our automated detector. The detectors are doing a really good job capturing these seasonal trends overall for Pacific wren and Swainson's thrush. It's biased a little low, but we know the direction of the bias, so it is capturing the trend. And then you can see with the Wilson's warbler, it's not really doing as well. We're failing to capture this late season bump in activity by this Wilson's warbler. And I can tell you, as the person who manually annotated it, that it's because these Swainson's thrushes are coming in and just totally drowning out the Wilson's warblers. Like you can sort of barely hear them as a manual annotator. So again, automated detection's tricky, and we're always dealing with quantifying uncertainty, and that's just part of the game in ecology, but pretty excited about applying this method. The other functions that I use every day pretty much from this package are the data visualization functions. They're really helpful for me for explaining the process to collaborators. It's really easy to show what the template looks like, what a mix of various detected events might look like, what labeled target signals and labeled false alarms might look like. And it's kind of nice to have this data summary figure as well, where you're looking at which template we used, what was the mean of every single detection, what was the mean of every single target signal, what was the mean of every single false alarm. I think it just helps kind of translate some of the concepts to folks who don't have their heads deep down into automated detection the way some of us here do. And then the other thing about this package that really has been a lifesaver for me that I haven't even talked about really today is the database. So we spent a lot of time thinking about like which tables do we need? What are the primary keys? What are the foreign keys? We use a SQLite database framework, and it's really been a lifesaver. I mean, you might have a ton of focal species, a bunch of different monitoring locations. You're monitoring deployment of various equipment that's breaking sometimes and getting reserviced. You have a library of different calls and templates and recordings, and it's a lot to manage. So the database is the least glamorous part of the software, but it's probably the most useful part. The SQLite database does require, we do force you to do some work up front as a user to really define your target species and your sounds. It does take a bit of setup. So I guess that kind of circles back to the point that it really is meant to be management objective driven. It's not exploratory software. There's other great software for that. But yeah, so I guess the next thing to point out is that AMMonitor is getting an update. So these are some slides that Larry passed along to me. So currently, as it stands, AMMonitor is just like a local database that you have to yourself. And this proposed model is that each project is going to maintain a local database, but then it's also going to be synced with ScienceBase, which is US Geological Survey permanent repository for all data. And this is kind of hearkening toward a vision where these labeled data, labeled acoustic data, and also in this case, labeled camera trap data could serve as a pooled resource for future machine learning initiatives. And so a generalized workflow here is that you have your independent monitoring projects. They're each using this unified framework, this unifying framework of AMMonitor. ScienceBase then serves as this stable repository, kind of like a data archival means as well. And then currently at the co-op unit, they're going to be working on a couple more initiatives, such as a Shiny app for labeling and summarizing data, and then also heading into this more state-of-the-art machine learning space and exploring TensorFlow. And this is their timeline that they're looking at for some of these initiatives. So maybe getting into some of these R Shiny and TensorFlow initiatives heading on next year. So that is about all I have to say for now. I've just a slide full of people to thank, plenty of folks from BLM and the National Park Service, Terry Donovan at the Vermont Cooperative Fish and Wildlife Research Unit, who's really the visionary behind all of this, Larry Klarfeld, who is a postdoc there currently, who's going to be taking this package into the future. And yeah, that's about it. I think that's all I have for you. So I'm going to see if I can access the chat here.
I can read you the question too. There's one if you can't find it. So the first part says very nice work, which I agree with that as well. It was a wonderful, clear presentation, and thank you so much. The question looks like it's related to the template detector. And so it's asking if you found similar spectral structure detected by 2 or different species with the template. If yes, how to deal with this. So I think basically, like, do you have 2 species whose calls are really, really similar? How do you deal with that with the template detector?
So I haven't run into that specifically in my work, but it's pretty, yeah, that's a great question. I mean, you would just be labeling, this species it's a false positive for this species. So it's not necessarily the most, I don't want to call it a naive approach. It kind of depends on what your question is. If you have a super similar species, then this might not be the right approach for automated detection. But I mean, the way I would deal with it is just to label it as a false positive if it's the confusing species, and maybe you would just have 2 different templates, and perhaps they'd be, perhaps there'd be, something enough to distinguish them, but I don't know. It's a good question.
I wonder too if you could have like a secondary step where you apply some sort of unsupervised cluster or something. I guess it depends again, like if they are actually super similar, it's just they're similar enough that the template detector isn't differentiating between them. So
yeah, I think it really depends. And I mean, I think with automated detection in general, it's like there are some approaches are going to work well for your problem and some just are not. So I'm definitely not putting this out as a catch-all solution, but it is a solution, an option. VJ, I see your hand.
Hi, Kathleen. Thank you for this presentation. This is really interesting. I also really enjoyed reading your paper on methods in ecology and evolution. So I work on tropical bird calls, and one of the big issues that we run into is either it's a lot of overlapping bird calls, or there's a lot of background noise. I wonder if that was something that you encountered with the work you were doing. And the reason I ask is because I use the monitor package, and I did try some of the cross correlation and the point matching approaches, but the precision and macro scores, F1 macro scores, were really poor. So yeah, I'm just wondering what your thoughts are on that.
Yeah, so I haven't worked so much I mean, something you'll notice about the system example I showed in the desert, like the desert's kind of a quiet place compared to like some of these dawn chorus areas that I've worked, that I've done field work in the East. And so I haven't run into that as much. I think an overlapping call, I'm not really sure how this system would do. I think it would depend on, how much training data you have. Cause like, I mean, if you've used the monitor system, then yeah, you've used that like baseline template system. It's hard to say, like, if you were to apply this type of machine learning routine to it and like refine it and see if it's hard to say whether it would improve it or not in a really, really acoustically dense environment like you're describing. So I don't know. It would be interesting to look at it, but I mean, I always think in that type of environment, maybe the state of the art, like the deep learning stuff is more the way to go, but I don't know because I'm less experienced in that arena.
Okay, thank you.
I have a question about your workflow. So it's so cool to see that you're actually using this stuff every day. But I'm curious because I have played around with the monitor package before, and it on my personal computers, it runs quite slowly. And so I was wondering if you could talk a little bit about how you are integrating the stuff, and if you're doing it on the, in the cloud, or kind of the processing part, and how that all works for you in practice.
Yeah, so I'm currently just running it on my, old slow laptop, and it is, yeah, it's maybe not the fastest. I also have tended to work on problems where I really only have a handful of focal species. I think if you have like a species richness problem where you're trying to detect every single thing that's there, then yeah, we would need a way better computational situation. And it might be more of a, job for BirdNet or something like that. But yeah, I usually just kind of let it run overnight, and yeah, and I don't know, Larry, and so we have Larry here too, Larry Klarfeld from Vermont Cooperative Fish and Wildlife Research Unit, who's kind of inheriting this, all this code I wrote and building on it and making it better. But I don't know, Larry, if you want to jump in on any of these ideas too, I know you're thinking about them as well.
Thanks, Kathleen. And this is a great presentation and great work. I'm happy to sort of pick up where you left off. To comment on the machine learning end of it, I think that the AMMonitor package is set up so that if there was an alternate classifier, it could be used in place of the template matching. But the nice thing about the template matching is it has like Kathleen said in the presentation, a very low barrier to entry. So if you're someone who doesn't have an expertise in machine learning, all you really need to do is find what looks like a exemplary template and select it. And you don't need deep learning. These state-of-the-art techniques require massive amounts of labeled data that A, might just be out of reach for some people who are trying to do acoustic surveys, and B, might end up in a situation where it's harder to work with the algorithm because of its complexity if it's trying to train a big deep neural network. So I think that for what it is, it really works well given its ease of use. But yeah, it's acoustic classification is a hard problem generally. So yeah, everybody is out there looking for better solutions.
Can I make one comment about the use of the template detector? And I agree 100% that a lot of times you don't need a more complicated approach, but it is for the template detector to work, the signals need to be quite consistent. So if there are, bird calls that it's just, changing and there's a ton of variability, the template detector is probably not going to be a great approach, right?
Absolutely not. Yeah, that's very accurate. I know I have a species of interest right now that I'm looking at in a park. It's the varied thrush. If you're familiar with varied thrush, they kind of do a, and they kind of are little DJs marching through different, and it's been way different from the Swainson's thrush, which is, well, I mean, they're a different genus anyway. But I'm not really sure that a template matching is going to be the right approach for that species. For exactly the reasons you just outlined. So it really depends. I think it always just depends on what your question is. And yeah, hopefully we'll collectively march toward maturity with automated detection. And I see Terry is on here too. Terry, I don't know if there's anything you want to hop in and mention, or if there's anything I missed that we want to make sure to emphasize.
Oh, just a great job, Kathleen, and I think you covered a lot of it, but we really are taking it to the next level, and that would be with Larry and Kathleen too, I hope. But as Kathleen pointed out in those slides, one of the biggest challenges is just the volume of data, and so moving the repository to the federal science-based repository as a way to store your images sort of kills two birds with one stone. The first is that it takes the burden of maintaining Dropbox or Google Drive or whatever, and puts it up in a repository. But the second big lift is then there is a way to keep these files for posterity, and it ensures that the metadata for all of the monitoring files has a long-term home. So that's what we're moving towards, and also really developing the photographic monitoring end of AMMonitor as well. As far as the speed, and Larry, you can jump in here too, but one of the things we're hoping to do is if the files are up on Sciencebase, that we can use some of the USGS computing clusters, so that as files hit science-based. They're run at the moment they're hit. So that would remove the burden of running your CPU and doing it in the cloud. But that's a longer term goal, but that's what we're hoping for.
Yeah, and I guess I will emphasize, because we have a lot of good discussion around, the appropriateness of a template-based matching system. But the goal is that, like, in this AMMonitor system, you could, in theory, use whatever type of detector you want. And then as long as you can fit it into like a scores table that fits into the packet, like the way we want the data to be organized in the database, you can use your own detectors. It's not limited to this. So yeah, I wanted to make that point, because I think that's a great discussion point, that the templates are not the right solution for every problem. Gio, I see your hand.
Yeah, hi, Kathleen. Thanks so much for this really wonderful presentation. I had a quick question just about the logistics of using mobile phones as recorders. And it's really great that you were able to like transmit data remotely over the cellular network, but I was wondering about sending data the other way around. So specifically, as you're progressing through the season and your different species are dropping in priority weight as you detect more instances, you need to update the recording schedules in response to that. So were you able to reply those updates remotely, or did that require manual servicing?
Yeah, that's a great question. So yes, so a big benefit of the smartphones is you do get that two-way communication. So we worked out the paper that I talk about related to that was a simulation, but we also worked out the mechanics in the field. So we were able to pull this off, where you're able to transmit the next day schedule to the phone. And you definitely, like, there are days where it's going to miss it, or the connectivity will be messed up. Like, in ecology, we miss stuff sometimes. But yeah, we were able to get that to work. And the way we make it work, so the phone will sit in airplane mode basically the entire day, and then it'll have a half an hour window where it's not taking recordings and where it can be transmitting recordings. But it's basically in connectivity for about a half an hour window, and it gets to transmit and it gets to receive instructions during that window. So it can be tricky to figure out, like, where do you want that window to be? You really would just do it at a time when you don't want to be sampling. But that's more or less how it works. And we did write a paper about the smartphone hardware setup as well, which should be in that resource sheet. And I might just put the resource sheet in here one more time. So if you're interested in learning more, all of the details are in the supplementary material.
Awesome, thank you.
Yeah, thanks for your question.
I have another question. I don't remember which species it was, but I think it was like the third one you were showing us, that the detector is just not working because there's a lot of overlap. And so I guess from kind of a applied aspect, like, what are you going to do about that? Like, what are you going to do to, like, are you just going to manually annotate everything, or?
Yeah, so at this point, I kind of pitched those 3 species as potential focals. So the park is interested in not only the overall phenology, and really the past work we've focused on using acoustic indices to characterize sort of phenological change. And we've had some discussions in this group about use of acoustic indices. They've got some benefits, they've got some drawbacks. I really wanted to look at finding a couple focal species that I thought might be driving the patterns in acoustic indices, so that we could make the indices a little more meaningful. So I kind of just chose those 3 focals, and I'm not sure the Wilson's warbler is going to be a good one overall. So we might just drop that one out and say, well, yeah, we know it's here, and it's going to get drowned out. And it's exactly the problem that some folks have already talked about, which is you're having overlap between calls or songs, and it's really not going to work for that species. So I think that I might just move forward with the thrush and the wren, since they're both kind of, not overlapping so much, and they have a canonical call that's not going to be changed, or song really that's not going to be changing. But yeah, good question. It might just be to drop that.
Okay, thank you. Yeah, no, I think that is really informative. And then it could come back to, like, what the overall goal of the project is, right? And so in this case, you're like, it's not working, so we can just focus on the ones that are. So
Yeah, it's interesting how you sometimes like circle in on like, is this really the question? And is this really the way to get to it? And if it's not, then it might be pruned out of the workflow. Yeah. And I guess one thing I will say, like a point that I wanted to make, I know sometimes I see other people's cool software and I think it's a really cool idea, but I don't really need that. I'm like, I'm not going to use it. And so if you're sitting here thinking, I don't know, it's some cool ideas, but I'm probably not going to use the software, I still encourage you, if you're an R user, like go in and look at the code. If there's anything you saw here that you thought looked interesting or cool, and like just poach the code if you need it. We've got GitHub repositories. We've got the GitLab, the packages on GitLab. If there's anything with visualization that you want to go in, like how did they do that? Go in and grab it and go forth and make cool conservation products and solve problems. That's my little, I guess, soapbox pitch. If you saw anything here that looked neat that you might want to adopt in your own work.
Okay, well, thank you. Does anybody else have any questions, either in the chat or? And I think we all really appreciate the Google Doc that you linked as well. Thank you for that. It's got a lot of really wonderful and useful resources.
Yeah, no problem. And again, if you know of anyone who might want to do a bioacoustics internship with me as a supervisor, feel free to pass that announcement along. Oh, thank you.
And I was just going to look through my email. I'm not sure what we have in 2 weeks from now. Does anyone on the call have it easy access? Well,
got it. Wait, yeah, I think we have a holiday break and then another holiday break. And then on January 18th, it looks like Magdalena Fuentes will present Sound Data, a Python package for the reproducible use of audio data sets.
Okay, fantastic. All right. Well, I guess happy holidays for those of us that celebrate. And thank you so much for your fantastic presentation, Kathleen. It was really wonderful. So
yeah, thank you all for attending and listening.
Bye.